topological sort. Topological sort in directed acyclic graphs or DAGs. Correct? So so what do we mean by topological sort? So firstly, what do we mean by a DAG? A DAG is a directed graph without any directed cycles. For example, an example of a DAG is something like this. Okay. And there needn't be just one, it could be one sink, there could be many sinks, there could be many sources, and so on. But nevertheless, we saw that any DAG, so let's define a source as a vertex of in degree 0 and a sink as a vertex of out degree 0. Correct? So this is a source, this is a sink, this is a sink, these are sinks. Correct? Does this make sense?
Yes, sir.
Okay. So so now we saw what topological sort was. Topological sort is a labeling of the vertices. So T from V of G to size of V of G, such that labeling of such that if U V belongs to G, topological of a DAG, not a graph, not just any graph, not just any directed graph, but a DAG G. If UV belongs to G, means that TU is less than T of V. Correct? Are you with me? And we also say that with distinct labels. Label of and TU is not equal to TV for all UV belonging to V of G. Correct? So basically, you would, for example, say, so 1 here, you could say 2 here, you could say 3 here because it comes after 1 and 2, you could say 4 here, you could say 5 here, you could say 6 here, 7 here. And here I'm doing it in an ad hoc fashion. Now, can I give this 8? Tell me. Or even can I give this 7? Is this 7 correct?
No.
No, because one of its predecessors is not numbered. So I should give 7 here, 8 here, then 9 here, 10 here, and 11 here. Correct? So this is a topological sort. Whenever there there's an edge, let's say this edge, its endpoints, it's from smaller to a larger endpoint. Correct? It's a renumbering of the graph, which is topologically sorted, so to say. Is the idea clear?
Yes, sir.
Okay. So now what is the, how do we find such a sorting? Firstly, is it unique, such a sort?
No.
No. What is a counter example? You can, for example, swap the labels of 5 and 3 here. Nothing will happen. Nothing bad will happen. And so on. So it's not unique. But notice that which vertex can be 1? Which is the first vertex? So which of the vertices can be 1?
Any source.
Any source can be 1. So any source can be 1. Correct? Here we give we could have given 1 to this and labeled. Correct? So now suppose you want to label a DAG starting at a number I, then you can label it, any source can be labeled I. And this immediately gives a recursive algorithm to label the graph. So topo sort I comma G, G comma I is G comma I, find a source of G, label it with I, remove I and all the edges incident on it from G to yield G prime. Correct? And then what do? Topo sort G prime comma I plus 1. Correct? Are you with me?
Yes, sir.
Okay. So another iterative way to write it, you can iterate it. You can say so you can say def iterated or topo sorted is while so while G is not empty, so you set T to be 1, or T to be 0, let's say, while empty, find a source V, TV is equal to T plus equal to 1, TV is equal to T, and then delete V and is incident on V to from G, and then iterate in the loop. Correct? So let's analyze this algorithm, this very naive algorithm that we have, and see how we evolve this into a more refined algorithm. So how much time does this algorithm take? Let's analyze this. So at every step you are reducing the size of the graph by 1. So how many iterations are there?
At most n into n minus 1 by 2.
N iterations.
Oh, inside the loop. Yeah. Got it, sir. Sorry. Yeah.
Every step you are removing one word. Correct? So, and how much time does one iteration take? 9. So how would you find the source V? You would have to have, you would, very naively, you would just, so how would you find a source V? So what is the source? The source is a vertex of degree in degree 0, correct? If you have in adjacency matrix representation, a source is a column containing all zeros. Correct? I mean, what is a column in an adjacency matrix? You have A, U, V. So AUV is 1 if there's an edge from U to V. If V is a sink, is a source, there are no incoming edges to V. So in this column, there is no U such that UV is an edge. So this is all zeros. This is all zeros, correct? So a source is a corresponds to a column containing all zeros. Is that clear?
Yes, sir.
Okay. So now how do you find this? Let's start from a very basic algorithm. So what is the time to, I give you the matrix and I want you to find me a source. So you will go for I is equal to 1 to n, for j equal to 1 to n, if if aij is equal to 1, then break. You will break this loop and so basically you would if a is equal to 1, you would say found equal to false. So and break, correct? Or you don't even have to do that. You just write, just break, correct? And you initialize found to found equal to false. If j equal to 1, break. Sorry.
There isn't a while loop better. Isn't a while loop better? While found is equal to false.
Yeah, you could do it through a while loop also. I'm saying you would say found equal to false here, and you would do a found equal to true in the beginning, and now if found then if found, then return I, correct? So this would and at the end you return -1. This would only outside this loop you would return. This would be only reached if the graph is empty or is not a DAG, correct? Do you agree with me?
Yes, sir.
Find source A. Correct? So what is the complexity of this?
Order n square.
Order n squared. Okay, good. So, so this already is order n iterations. Each iteration is order n squared, and we didn't do initialization. That would also take order n squared. So, but let's see. So delete V and edges incident on V from G. How much time does that take? So you would go through the column and row of V. So column of V is all zeros because it's the source. Correct? You would just go through the row of V and delete, make all of these zeros. Correct? So this would take order n time. So overall time taken by this algorithm is order n cubed. Correct? So the naive version of it runs in order n cubed time. Now can you improve this? So what are the optimizations that you can think of which would improve it?
Sir, could we maintain a list of degrees as well? Of in degrees and out degrees of every
Correct. So you could maintain the degree, the in degree of every node. Correct. So how would you do that? So now so you have to update these at every step. Correct. So how would you do that? So firstly, if you have the in degree of every node, how would you find a source? Just naively again.
we'd scan through the list in order n time and
Scan through
with
this
the
order n time. So this becomes order n. And now deletion of V and edges instead of this remains order n. But now we have to update this this in degree. So how much time does that take? That can be absorbed in this order n, because at every step you are looking at the vertices W such that VW is an edge. So you're looking at the row of V. You're looking at the row of V, and for every vertex, that every one here, you are decreasing the in degree of that, the corresponding W by 1. Correct? So decrement the in degree of every out neighbor of the deleted source. Correct? And this can be done in order n time. So this remains order n, and now this becomes order n squared. Do you agree? Do you agree with me? Is there anybody who is confused about this?
Sir, I did not understand how it was order n square. Like,
So there are n iterations. N iterations of this, because at every iteration you're removing one vertex, one source. So there cannot be more than n iterations, correct?
yes.
And every iteration takes order n plus constant plus order n time. So it takes order n time. So overall there are order n into n order n, which is order n squared time. Correct?
Okay. Okay. Thank you, sir.
Okay.
How you found the source in linear time?
So you maintain the in degree of every node. To find source, so if you have the in degree of every node, you can scan the in degree list and report a vertex with in degree 0. Of course, you might say that if this vertex has already been considered before, then how do we distinguish between that vertex and a vertex that has not yet been considered? So you mark that also. Correct?
Yes.
So scan the.
Sir, is the list with in degrees given along with the adjacency matrix?
No, you are creating the in degree. So that's a good point. You are creating the in degree list, and how much time does that take? So to create the in degree list, you have to go through each column and update the in degree of that vertex. The number of ones in that column, you have to sum up, and that takes another order n squared time.
Okay, sir.
Correct? I should have written this with a different color, but yeah, it's too late to do that now. So is this clear? So overall the time is order n squared. This includes the order n squared time for computing for initializing in degree list. Correct? Any questions? So now in BFS and DFS, we saw that we could get something like order m plus n time. Can we get order m plus n time for topological sort also? So how would we do that? Indeed, we can, and let's see how to do that. So, what was the crucial observation in BFS DFS that allowed us to give an order n squared time, order m plus n time algorithm?
We considered the edge list. We considered the edge list.
We considered the yes, the edge list, the adjacency list. So okay, so again we switch from adjacency list, adjacency matrix to adjacency list. So adjacency list instead of adjacency matrix. So now what happens? So now how much time does it take to initialize the degree in degree? So what do we mean by adjacency list? Usually you mean the out neighbors of a vertex V. Okay. So you have the neighbors of vertex V, the out neighbors of vertex V. Every V, you know what are the W's that it is connected to. If this is our notion of adjacency list, then how much time does this algorithm take? So let's see. Finding a source. So finding a source means for in degree list. How would we So how would we create the in degree list? I mean, one way to do it is for each vertex V, in degree V equal to 0, initialize it. For each vertex V, for each out neighbor W of V, in degree of W plus equal to 1. Correct? So what is the running time of this algorithm or this initialization? There are two loops, two nested loops, and yet we see each. So you would think that there are two nested loops and that takes n squared time. But no, the point is that you are going over each edge exactly once. So it would take order m plus n time. This takes order n time. This takes order m plus n time. Overall time taken is order m plus n. Are you with me?
Yes, sir.
Okay. If there's any confusion, ask me.
So just to confirm, it's the first loop, sorry, the one on top which takes n time, and the one on the bottom, the nested thing, that entire thing just takes n time, right?
No, it takes m plus n time. You anyway have to spend one time at least for the vertices for each vertex. So this takes order m plus n time. This takes order n time.
So why are we spending time on each vertex in the second thing? Like,
You're going over all the vertices. So you are basically spending, if it has no neighbors, you will spend one time. If it has dv neighbors, you will spend dv time. So the
I
time
see. Okay, right.
summation dv plus 1. V dv is the out degree of v. D plus v is the out degree of v.
Yes, sir. Got it, sir. Yeah, thank you, sir.
Is equal to order m plus n. Correct? Thanks for the question. Out degree of v. Correct? So,
Yes, sir.
So now this list is ready, and now how do you find a source? So this in list, instead of order n squared, we can do it in order m plus n time. And now you want to make this finding a source efficient. Of course, if you scan this in degree list, it will take order n time to go through the list in any case. But if you maintain a data structure in which you keep the 0 in degree nodes, which you record the 0 in degree nodes which have not yet been processed, what is such a data structure? You can keep it in a queue, for example, correct? So, in this one, you say, so let me write it from scratch. Def topo sort matrix G. Q is equal to empty. T is equal to 0. And for now, I put this code there. Correct? So we have created the in degree list, and now for each V in V, what do we do? No. For each V, no. So while Q is not so. Sorry. So for each V in V, if in degree V equal to 0, Q to be Q union V. Q dot append V. So we add the sources. So what does this do? Is add sources to Q. Correct? Fine. Now we have the Q, and while Q is not empty, what do we do? Let V is equal to Q dot extract. So you remove one vertex from V, whatever this function call you call it, V Q dot extract. And now what do? We for each vertex, for each W in out list of V, what do? We do in degree of W minus equal to 1 if in degree W equal to 0, then so I should call this in Q. So in Q and call this DQ. If in degree W equal to 0, then Q dot in Q W and yeah, and what else are we using here? In degree is so out list of so so and that's it, correct? And of course this labeling. So we had put t equal to 0, we say t plus equal to 1, t of v is equal to t times give the topo sort number, the topological number t to v, correct? Correct, and that is our entire thing. So let's say t is the thing that you get out of topo sort. you can say for P equal to I is equal to 0 to I equal to 1 to n, TV equal to 0. So are you with me? Does this make sense?
Sir, like, how do we show that it will cover all the vertices in the graph?
Okay, good point. So how will it cover all the vertices in the graph? So if it doesn't cover some vertices in the graph, then at that point, the Q is empty, correct? Which means there are no sources in the graph. But if there are no sources in the graph and the graph were a DAG, that is not possible. Correct?
So
Okay, okay.
could you repeat what you said?
Tell me.
No, like could you repeat what you said about for DAGs?
So I'm saying last time we showed that every DAG must have every non-empty DAG. Non-empty meaning with at least one vertex. So every non-trivial DAG must have at least one source, correct? And all the sources which have not yet been seen are on the list. This is one thing. Every source, every current source is on, which has not yet received T value is in the queue. This is an invariant we maintain, correct?
Yeah.
So if the queue becomes empty, means that there are no queues, sources in the graph remaining. But every DAG must have at least one source, means the DAG must be empty.
Yes.
At this point. So everything has been labeled, correct?
Yes, sir.
Okay, and what is the running time of this? I claim it is order m plus n. Why is that so? So let's go at it from the beginning. So this takes order n time. Let me write it on the left side. Color. Use this earlier. Order n time. This is again order n time. For this we saw is order n plus n time. But each vertex v in degree v equal to 0, q is 0. This is order n time. We are just single loop. So this one is so I claim this entire thing runs in order m plus n time. Why is that? Can someone tell me?
Sir, every vertex enters and exits the queue once.
Every vertex enters and exits the queue once, and every edge is seen exactly once. This inside this, for each W in out list of V, meaning when V to W is an edge, this edge, this set of instructions can be attributed to this edge, correct? I mean, you will, whenever there is an edge from V to W, you decrement the degree of W by 1 and you NQ W. So this takes, if in degree of W is equal to 0, then you NQ W, correct? So this is an order 1 time operation which can be attributed to this edge. And there are order m edges. So overall, this takes order m plus n time. And this is again order 1 time. So totally this takes order n plus n time. Are you with me?
Yes, sir.
Questions?
Sir, about the first m plus n again. I thought I got it, but where did that plus one come from? If the I see it when the vertex has no out neighbors, but if the vertex has out neighbors, why
You
are we
can
not
think
doing
of-
it? Yes, sir.
You can think of it this way. Suppose d plus is the degree of v, out degree of v, correct?
Yes, sir.
You can think of as spending time d plus v plus 1. This expression works even if d plus v is 0, correct?
Yes, sir. But
Hmm.
if like we don't have many vertices with out degree 0, would we be able to get a better bound?
But it will be offset by this order n in any case. Suppose
Right.
none of the vertices has degree, or only one vertex has degree 0. I agree, it will take order m plus 1 time overall.
Okay. Okay. That is what I wanted to clarify, sir.
Yeah.
I get it now. And we would anyways be taking m plus n because other things take
We
it.
would anyway be
Yeah.
spending order. Yeah. Correct?
Sir, yes, sir. And just to finally clarify, the for loops do not take any time here, right? Because we're not actually checking anything. That is like, yes, sir.
For loops do not take any time, meaning I don't understand that. For loop is this entire thing, correct?
Yes, sir. I phrased that badly. I mean that the only time it takes is the instructions that we're doing, like just stating the for loop. Okay.
Or you can think of it as order 1 time per iteration of the for loop. That you can think of as, that's why I wrote once again. Hello? Hi, can you hear me?
Yes, sir.
Yes, sir.
And can you see the screen? Sorry, something happened. I just, yeah. Yeah. So this plus 1 is for all these things, correct? For each vertex
sir.
v, you are spending 1 time at least in iterating over for all v, correct?
Okay, sir. Okay. Yeah.
Correct. So what over and above whatever is spent inside, you spend 1 time, order 1 time.
Okay, so we are spending order 1 time just
Yes.
to.
Yes.
Okay. Okay. So
because instructions are being, there are instructions there, correct?
okay. Okay.
Hmm.
Okay. Thank you, sir.
Okay. More questions? Okay. So we could also have maintained an in list, which we skipped doing at an intermediate stage. We could have maintained the in list of V, correct? And that would have allowed us to maintain the degree and so on. But yeah, that is the intermediate state. So this is the final algorithm that we get, correct? Now, let us take an example and see how does toposort work on this. Let's take this example. And let me expand this. and A, B, C, D, E, F, G, H, I, J, K. The some numbering of the correct. So initially in your queue, you would have so you are enqueuing here and dequeuing here. You enqueue K and then you can enqueue A and then K, and then you dequeue A. Say so, you would give this the number 1, and then its neighbors. So you would remove this. Now, is there any new source form? Not yet, because so this is removed from the queue, and let me draw a longer queue. Okay, so no new sources are added. The degree of B becomes, so I should have written the degrees earlier. In degree is 0, in degree is 0, in degree is 2, 2, 2, 2, 1, 1, 2, and 1 and 2, correct? So now we take out K and we update the, so firstly we had updated this to 1 and updated this to 1. Now we take out K and we update the degrees of its out neighbors. So B becomes 0, and therefore we insert B in here, and J becomes 0, so we insert J here. We enqueue J here, correct? And now this is gone. This is gone, correct? So now the things are J and B, and now we take out B, and its out neighbors are C, it becomes 0, and I, which becomes 1. Correct? And now C is put in here, and now I remove, so I should have given them numbers, but the numbers are in the order in which they are taken out from the queue, which is written here. So that's fine. So so this is 1, 2, 3, 4. So J is, where is J? J is here. J is removed, and its neighbors are I is set to 0, and therefore I is put in the queue, and this is set to 0, and H is put in the queue. Correct? Now you take out C, so C gets the number 5, and now its neighbors are D, only D, and nothing is put in the queue. Now you take out I, and you set its neighbors. This is set to 1. That is the only out neighbor. So this is set to 1, and this gets 6. And then what happens? J is already gone. Yes, so J is gone. Now we take out H. H is, so we remove H, that gets 7. And its out neighbors are E, which gets 0. So E is put in here. And G, which is also put in here. Correct? And now we take out E. So E, this becomes 8, and this becomes 0. This becomes we add this becomes 0. We add when we took out E, we should have G. We took out E, we should have added D. Yeah, D. And now we remove G and we add F. This is already 1. When we remove G, it becomes 0. And now this is F. And now we take out D and F one by one, and they get 10 and 11. Correct? So this is a topo sort. This is 1. K is 2. B is 3. J is 4. C is 5. I is 6. And H is 7. E is 8. G is 9. And D and F are D is 10 and this is 11. Correct? And you can see that all the numbers, all the arrows are coming top to bottom. So it's a DAG in that sense. It's in fact an upward planar DAG, and all the numbers are increasing downwards. So it is a valid topological sort. Correct? Are you with me?
Yes, sir.
Okay. Now we have this topological sort. Correct? Now, what can you, what uses are there of it? So we were talking about doing courses at CMI or courses anywhere which have prerequisites. Correct? And we said that we would model the prerequisite arrows by arrows in this diagram. Correct? So if B has a prerequisite A, we put an arrow from A to B. Correct? So if A is a prereq of B, then put A comma B in the graph. Correct? Correct? And now you want to know what is the earliest time in which you can finish the degree, assuming that you can take as many courses as you want in a semester. But you cannot take a course which is a prerequisite of some course in the same semester or in the same semester, correct? So all the courses must be taken after their prerequisites. Each course must be taken after all its prerequisites have been taken in one of the previous semesters, correct? Is the problem clear?
Yes.
So what is the earliest semester? Let us define earliest of C is equal to the first semester in which course C can be credited. Now, how would you compute earliest of C? So, what is the recursive way of computing earliest of C?
So we
So
can
tell me.
we can modify our first tupple sort algorithm, and instead of marking separate things, we mark everything in the same
No,
place.
no, no, don't give me an algorithm first. I know you know the algorithm, but instead of that, can you tell me how do you compute it? What does it mean to compute it? So what I'm saying is if requisites of C are P1, P2, Pk, correct? Then earliest of C is equal to the maximum earliest of P1, earliest of Pk plus 1. Do you agree to this? The prerequisite, the last prerequisite that finishes after one semester after that, you can complete C. Do you agree?
Yes, sir.
Okay. Now my question is, what does this have anything to do with topological sort? Why am I talking about this at this point?
Like, shouldn't it be minimum? Like,
Which one?
or instead of max?
Okay, let's see. So you say that C has preregulates P1, P2, P3. P1 suppose finishes in, it's a source, finishes in first semester. P2 finishes in fourth semester, and this finishes in second semester. Now, when can you take C?
Oh, I see.
You would take it in the fifth semester, correct? So now the point is, this relates to DFS because if you know the order of, so you can compute. So of course you could compute this earliest directly by looking at all the. This is a dynamic program. If you don't know what a dynamic program is, you will know soon enough. But so if you knew all the earliest, so this is a recursive equation, correct? But it is much easier to solve this if you have access to the topological sort. In fact, in the topological sort, you can just find the earliest value, like someone was telling me just now. So how would we do that? So tell me, where would I, so of course I can initialize earliest V is equal to, let's say, infinity, correct? Now, I claim that if in degree W equal to 0, at that point I put earliest of W is equal to earliest of V plus 1. Would this work? I claim just this will give you the entire thing. No comparison, nothing. This is the only thing. Why would this work?
Sir, could you repeat this once?
So I said that earliest we initialize to 0 to infinity everywhere, correct? Or we don't even need to do that. Infinity everywhere. So here I say earliest of V equal to 1, correct?
Yes, sir.
So basically, I'm saying that every time you enqueue something, you you set its earliest value.
Okay. Okay, got it, sir. Thank you.
Correct. So, and why is that?
So because we're adding something to the queue when in our example when it doesn't have any prerequisites, we only add it to the queue then.
Exactly. When all its prerequisites are done, and V was the last prerequisite to be done. Correct. Because otherwise it would have been added earlier. The in degree of W would have become 0 earlier. Correct. Correct. So the last prerequisite, when it's done, at that point you initialize it. Correct.
Yes, sir.
And just one more remark, and then we'll be done for today. So what does earliest compute in the graph? If I give you a die, what does earliest compute? As a graph theoretic property, what do you think is earliest computing? I claim earliest V is the length of the longest path ending at V. Can you prove that? Minus 1 or something. This V is equal to length of the longest path ending at V minus 1. Plus 1, sorry. Plus 1. So basically for sources, earliest V is 1, while the length of the longest path ending at V is 0. And thereafter you add this plus 1 at V, correct? So how would do you see this? You could prove this by induction, of course. Do you agree? By structural induction on the vertices, you can prove this. Are you with me? Anybody?
Sir, can you just briefly say the argument?
So the argument is, suppose you have so I want to prove that length of the longest path ending at V plus 1 is the earliest of V, correct? So we have to show earliest of V is less than equal to this right hand side, and right hand side is less than equal to earliest V, correct? Now, why is earliest V less than equal to so you take the longest path to V, correct? Now V cannot be done. So suppose the path is 1, 2, 3, some EV, correct? So firstly, correct? So it contains EV many vertices. So you cannot complete it with less than EV minus 1 things before it. Now, are you with me?
So, sir, like, so we're saying that there does not exist a shorter path than this, right?
There is no, all the paths are shorter than this. All the paths to V are shorter than this path, than the earliest path.
Okay.
So I'll let you think about it.
Okay, sir. Yeah, I think.
Correct. So more questions? If not, then we conclude today's lecture. And okay, so we meet again on Thursday, and there'll be a quiz on Thursday. Okay, thanks. Bye.
So will it include today's class thing too?
Let me see. Okay, no. Let's not include today's class.
Okay.
Okay. Okay. Thanks. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.